Yeah, welcome. So in the last lecture, we have discussed about various uninformed search techniques. Sorry, informed search technique, that is the heuristic search techniques. So with what we have discussed in the last lecture, with that we'll be stop discussing the heuristic search techniques. Now we'll be moving on to the next topic, which is local search and optimization problems. First, let us try to understand what is meant by local search. See, in a local search, the algorithm will not remember the nodes which were generated earlier. That is, the algorithm will always remember only the current state. Whatever the previous path, it will not remember. It will forget that previous path. Such algorithm is called as local search. So initially when the algorithm starts, it will start from the initial state. Now initial state itself is the current state. Now from the initial state, it will go to the next state. So whatever the next state, we'll call it as current state. So this is the next state when compared with this. But once it reaches the next state, this won't be available in the memory. Now from the current state, it will try to move to the next state. After reaching the next state will become the current state and this will be removed from the memory. So this process continues until it reaches the goal state. So this is such algorithms are called as local search algorithm. So why we are interested in local search algorithm? Why are we ignoring the path? So the answer is, for most of the real-time problems, the path is not required. We need only the solution. So the path of reaching from the initial to the goal state is not required for most of the problem, not for all the problems. Say for example, 8-coin problem. Initial state can be anything. Initially, there can be 1 coin on the board or 2 coin on the board or all the 8 coins on the board in different locations. But finally, we want one board position where 8 coins will be on the board and they will not get attacked. That's it. We don't want any path like move this coin there, that coin there, so that you will get this combination. No, that is not required. Finally, we want a board position where all the 8 coins should be placed and they were not attacking each other. Similarly, there are many problems for which we are not bothered about the path at all. Say this, what you call, say this uh, uh, eight puzzle problem also. We somehow we want to bring it to the goal state. The path need not be remembered, but there are certain problems for which path is to be remembered. For example, a traveling salesman problem. If you take the traveling salesman want a path. In what path, if he reaches, he will reach all cities in the least cost, right? But there are many problems for which we need not remember the path at all. So when we don't remember the path, when we need not remember the path, the memory complexity, I mean the space complexity of the algorithm, it will get reduced drastically. Okay, and in most of the problem, and for most of the problems, we need only a good solution. We don't need a best solution. So such problems are called as optimization problems. And in the real time, it is not always possible to identify the best solution because the state space may be very huge. So it is enough to get a good solution. So that's what we are going to discuss in this topic, local search and optimization problem. So we'll be so this local search and optimization problem can be achieved by using different techniques. All those techniques we'll be discussing. First, we'll be discussing an algorithm called as hill climbing algorithm, and we'll be discussing several variants of this algorithm. There are 3-4 variants of hill climbing algorithms. All those variants we'll be discussing, and then we'll be discussing another algorithm which is called as simulated annealing. This is also an example for local search and optimization algorithm. And then we'll be discussing another algorithm which is called as local beam search. Okay, and 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 at last we'll be discussing about genetic algorithms. Right. So this is the flow of the lectures. Okay. So let us start with. So this is uh, what we have discussed so far. In many optimization problems, the path to the goal is irrelevant. The goal state itself is the solution. So we don't want the path at all. So in such cases, we use local search algorithms. For example, finding a configuration satisfying certain constraint. Example, the 8-queen problem, or job shop scheduling, in the sense in a job, or in a shop, scheduling, like worker scheduling, like which person should work from what time to what time, right? So if you want to schedule that, say a shop is running for 24 hours and there are 5 or 6 employees, and then who should work from what time to what time? So we need a final solution. We don't need any path at all. Or say, for example, the timetable which you are following. What is first hour? What is second hour? From Monday to Saturday, there is no path required here. Finally, we need the set of entities, set of values here, like uh, which class is at which hour. So these are some of the problems for which the path is not required. We are only interested with the solution. So in such cases, we can use iterative improvement. Start with a single current state and try to improve. So we start with the initial state, that is the current state, and then we improve. After improving, we reach a new state that becomes the current state. Now we need not remember the past. So continue like that, right? But traveling salesman problem, that's not an example of this category. In case of traveling salesman problem, we need the path also. Okay. So what local search algorithm does? It picks a solution from the search space and evaluate it. So what will be the initial state? So initial state, actually, in most of the local search algorithms, there will not be any specified initial states. Somewhere it will start randomly. There is no specified initial state. Somewhere it will start randomly, so that we say that pick a solution from the search space. So say the search space is nothing but the problem space. So the problem space contains, assume the problem space contains many solutions. All these are solutions. Okay. But some of the solution may be, so basically all these are solution, but some of the solution may be more accurate, some of the solution may be less accurate, some of the solution may be somewhere in between. So choose one solution randomly and evaluate it. Evaluate means you identify how good this solution is. Okay, that is, compare with your goal state. You know what is the goal state, compare with that. So how much it is away from the goal state? I mean, that is called as error. Calculating the difference between the goal state and the initial state is error. So check it, how much the error is. So so as we have picked this randomly, so it is highly likely that it will have more error. Then we'll call this as current state. Okay. Now from this current state, we have to identify a better state than this. Apply a transformation to the current solution to generate and evaluate a new solution. So we call this also as a solution. It is not that this is not a solution. This is a solution, but its score or its fitness is very low. Its score or its value, it's whenever we evaluate it, whatever the value we got is very low. So now apply some transformation to this current solution and generate a new solution, right, which is better than the current solution, and evaluate the new solution. So first generate just a new solution, and first generate a new solution and then evaluate the new solution. Okay. If the new solution is better than the current solution, then exchange it with the current solution. So this is what it does. So initially we generated a random solution and that we called as current solution. Then we create a new solution and then we evaluate the new solution. If this new solution is better than the current solution, then we call this as the current solution. Okay. Then we call this as the current solution, and whatever the previous current solution was there, that will be discarded. Sorry, something wrong. So whatever the current solution, that solution will be discarded. So this will be discarded and this is the current solution. Like this, the algorithm will, so this is step 1, step 2, step 3. Keep repeating step 2 and step 3 until you reach the goal state. Okay. So I think the point is clear. So in the state space, we consider everything as a solution, but different solution will have different score or fitness or or the result of evaluation function, whatever you call it. So we randomly pick a solution and then we call it as the current solution. From the current solution, we apply some transformation function and we create a next solution, create a new solution, and we check whether the new solution is better than the current solution. If the new solution is better than the current solution, then call this new solution as the current solution and discard this current solution and repeat this process. Suppose if new solution is not better than the current solution, then also continue. Then also uh, then we won't call this new solution as current. Then we discard the new solution. Again we'll repeat step 2 for the current solution. Create some other new state for the current solution and check whether this is better than this or not. If it is better, call this as current state and discard this. Otherwise, call this itself as the current state and continue. So this is the overall working principle of all local search algorithm. Okay. So basically, the local search algorithm, it works only with the current state and generally move only to a neighbor of that state, right? So from the current state, it just moves to the neighbor, and once it finds a better neighbor, it discards the the past current state, and the better neighbor becomes the new current state. Whereas if you consider the Esther algorithm in the heuristic search technique or informed search technique, the algorithm used to remember the paths, which is not required here. At each step of the local search algorithm, see, this is interesting. At each step of the local search algorithm, we have a complete but imperfect solution to a search problem. What does it mean? Why we call it as complete but imperfect solution? So we what we said in the state space, we consider everything as a solution. So these state space contains set of possible states for the problem. So every state is treated as a solution. Now, some solution may be more appropriate, some solution may be less appropriate. Okay. So this less appropriate solution. So when you call this is the goal state, then this is a more appropriate solution, or it is a more perfect solution. It is a perfect solution. But say some other solution which is not a goal state, then this is also a solution, but this is an imperfect solution. But this is an imperfect solution. So everything is a solution, other than the goal state, remaining all or nothing but imperfect solution. Right? So what is meant by complete? When we call an algorithm as complete, an algorithm is complete if it will find a solution. Okay, if a solution exists and if it finds, then we say that algorithm is complete. So in our case here, we consider everything as a solution, but other than the goal state, all the solutions were imperfect solution. So what we can say, the local search algorithm, at every step it is sure that it will find an imperfect solution. Okay. So we can say that it is complete but imperfect. Complete means it has found a solution, but it is an imperfect solution, right? Because what's the definition of complete? We call complete means if a solution exists, it should find. So here also it is finding a solution, but this solution is not a perfect solution, right? So at each step of the local search algorithm, we have a complete and imperfect solution. Complete means as it is a solution, we call it as complete. But this solutions uh, is not a perfect solution, so it is called as an imperfect solution. Okay. So whereas in Esther algorithm and all, they are not called as complete solution. They are not called as imperfect solution. They are called as partial solutions. In Esther, we have a path, right? If you start with Arad, then Arad to Sibiu. So this is one path. So you say your objective is to reach Bucharest. So if you have reached up to Sibiu, or if you have reached up to Fagores, from Sibiu to Fagores, then this is called as partial solution. This is not called as imperfect solution. But here, every state is called as an imperfect solution. Okay. As every state is an imperfect solution, at every step, the algorithm is said to be in complete uh, uh, but imperfect solution. At every step, we have a complete and imperfect solution. Okay. So what are the advantages of local search algorithm? So these are the advantage. Constant space, that is memory requirement is constant, because always the algorithm need to remember only one state. It need not remember anything more than the current state. So the memory requirement is always constant. It is neither linear nor exponential. It's just the constant memory requirement. It is suitable for both online and offline problems. Online means real time problems. In real time problems also you can apply, uh, because of its memory requirement, it does not demand more memory. Or it can also be used for offline problems. It can find reasonable solution in large solution spaces, that is state spaces, where exhaustive search would fail miserably, right? So it can find reasonable solution in large solution spaces where exhaustive search would fail miserably. Exhaustive search means the search techniques which are used by what you call the search techniques which are used by uninformed heuristic technique, or even informed heuristic search techniques. Those are called as exhaustive search technique. Actually, these algorithms, they behave in a different way, right? So even if your solution space is very huge, it can find a reasonable solution uh, where exhaustive search would fail miserably, because they may not end up with a solution. So these are the major advantages. So so the first is about the space. The second is about it can be used for both online and offline problems. The third is it is about time. It is time. So it can find the solution. It can find a reasonable solution even in a large space, in a large solution space, where a normal exhaustive search algorithm may fail. So so this is a pictorial representation of the local search algorithm. So let us, so here instead of calling a state space, we call a solution space. So what are the possible states? That is, instead of calling as a state space, it is called as a solution space. So for a given problem, assume these are the possible state space or solution space. Then the algorithm, what it will do, it will randomly choose one solution. It evaluates its value. Our goal may be somewhere here. Okay, then the algorithm will check, identify something nearer solution. It checks whether this is better than this or not. If this is better than this, then make this as current state, and again continue and keep moving until you reach the goal state. So this is how the algorithm works, right? Traveling salesman is that this is not an example for what you call for local search algorithm. Let us skip this. Let us go to the next. Yeah, yeah. So when you consider the local search algorithm, we can it is better to understand the local search algorithm by considering the state space or solution space as a landscape. So let us consider the state space or the solution space as a landscape, right? So this is a land, okay? So which contains some hilly areas. Say so in this land, this part is called as global maximum. So if this is the solution space of the problem, then this is the global maximum. Global maxima means this is the best point. This is the best point. So this is the goal state. There is nothing better than this state. Okay. And this point is called a shoulder. Why it is called a shoulder? Because or before shoulder we'll have this. This point is called as local maxima. Why it is called as local maxima? See, in this area, if you see in this area, this is the maximum point. So in this area, this is the maximum point. But if you take the whole state space, this is not the maximum point. This is the maximum point. In the entire state space, this is the maximum point, which is called as global maximum. But in a limited area, this is the maximum point. So this is called as local maximum. Okay. And this area is called as so this is also a local maxima, but this is a flat local maxima. Again, if you see in this area, let us take this area alone. If you take this area, this is a small peak. So this is a local maxima. But in this place there is a flat, like, so it means there are many solutions lying here, 1 2 3 4, but all these solution having the same fitness score. That is, if you apply an evaluation function for all these solutions, they will give the same value. But all these are lying at different places, so it is called as a flat. But here that is not the case. Only one solution is at the top. The another solution may be here, another solution may be here. So when you compare this solution with this solution, this is better than this, here this is better than this, right? But here that is not the case. Multiple solutions, or we have multiple solutions with the same value or same score. Okay. uh, and, and and that point is also a peak point in a limited area, so that is called as local maximum. Okay. This is called a shoulder. So what is the difference between a local maxima and a shoulder? So a shoulder is something, after a certain point of time in any one of the direction, it will start improving, it will start increasing. That such an uh, such a place is called a shoulder. Whereas in local maxima, it is never increases after. See, in this local maxima, in this flat local maxima, if you keep travel, after a period of time it will decrease in this direction. In this direction also, if you keep travel, it will decrease after a period of time. So if you are in local maxima here, then you travel in either direction, you will only go down. If you travel this way also, you will go down after a period of time. If you travel this way also, you will go down after a period of time, right? Whereas in this case, that is here, that is not the case. Of course, assume that you are currently here. Now if you travel this way, after a period of time you will go down. But if you travel this way, after a period of time you will go up, and it is highly likely that you will reach the global maximum, right? So our ultimate objective is to reach the global maximum, because this is the best point. There is no other best solution than this. Okay. So this is so here we are understanding the state space with the analogy of landscape. So that's the point. We are understanding the state space or the problem space with the analogy of landscape, right? Okay. So one more important thing is here. See, here we have discussed that our objective is to maximize. That is, we want to identify the global maximum. But always that is not the case. Say let us assume the object. Say let us assume uh, uh, the problem is evaluated based on cost. Let us assume the problem is evaluated based on cost. In that case, what you want to do, cost should be increased or decreased? Cost should be always decreased. So in that case, we want to reduce the cost. So if you want to reduce the cost, then you have to find, your objective is not to find global maximum, then your objective is to find global minimum. Okay. So if the problem is evaluated based on cost, then our objective is to minimize minimize the cost. Then our objective is not to find global maxima, our objective is to find global minima. So in this landscape, probably this is the global minimum. So this point is called as what? Global minimum. Okay. Right. And this is a local minima, because in this area this is minimum, but this is not the overall minimum point. So this is a local minimum, right? Okay. So if the problem is trying to uh, what do you call, if the problem is evaluated based on cost, then your objective is to find the global minimum, right? If the problem is an evaluation function, if it is an evaluation function, then normally we want to maximize the evaluation function. In that case, we have to find the global maximum, right? Okay. So first let us so this is the first local search algorithm which we are going to learn, and this algorithm is called as hill climbing search algorithm. Hill climbing, there are several versions of hill climbing search we are going to discuss, and this is the simplest version, which is called as uh, gradient steepest ascent, which is called as gradient steepest ascent, or it is simply called as steepest ascent hill climbing, right? So this algorithm, like how what we have discussed for the generic local search algorithm, it works that way. It just randomly selects one solution from the search space, then it identifies next solution, new solution, checks whether the new solution is better than this current solution. Then the new solution will become the current solution, and then next it proceeds that way, right? So let us try to understand this algorithm. Function, the function name is hill climbing. It takes a problem as input. What it is going to return? It will return a state that is a local maximum. So most probably this algorithm cannot give an global maxima as the output. It depends on the initial state from where it is starting. But in most cases, it won't get into a global maximum. So let us assume that it is going to return a local maximum as the output. So as we already discussed, here our objective is not to find the, if you are able to find the global maxima, that is fine. But most of the cases it may not be possible. So most of the time it is enough if you are settling with a good solution. So local maxima is treated as a reasonably good solution. What is the input? So input is the problem. The problem itself is the input. These are the local variables. Current represents the current node, and neighbor represents the neighbor node or the next node. Okay. So we are creating a current node. What we are doing, make node random state problem. That is from the state space. So this is the state space. From the state space, we pick up any one state randomly. From the state space, we pick up any one state randomly, and that state we are calling as current state. Okay, make node random state from the problem or from the state space. We pick up any one state randomly, and we make a node for that, and that becomes the current node. Then we do this loop. During this loop, what we are doing, neighbor equal to highest valued successor of the current. Okay, so so let us say that we have a current state, some state is there, so that is the current state. Now we are generating a neighbor for the current state. And what is the neighbor? The neighbor of the current state is the one which has the highest values among the successor. So from the current state, there are many successors. Out of all these successors, you pick up the one with the highest value. Okay, so let us identify one with the highest value, and that highest value we are calling as neighbor. Okay, but still we don't know whether this highest value is better than this current state or not. So next we have to compare. If value of neighbor, the value of the neighbor node, if it is less than or equal to the value of current node. Okay, if value of neighbor is less than or equal to current node, then it means that current is better than the neighbor, right? Whatever the chosen neighbor, then we return the current, because the current node is better than the neighbor. So we need not move to the neighbor. Otherwise, suppose if this is not true, if value of neighbor is not less than or equal to the value of current, it means value of neighbor is greater than current. In that case, current becomes the neighbor. So current node will become the neighbor becomes the current. So the previously whichever the neighbor node, that will become the current node, and the algorithm continues that way until, so it continues until it reaches the till it reaches the goal state, right? So this is the working concept of what you call steepest ascent hill climbing algorithm. So this is a very simple algorithm. So let us see in this landscape. In this landscape, let us see. For example, if the initial state is this. For example, if the initial state is what you call, if the initial state is this, or the initially how the initial state is identified. Some randomly we pick something from the state space. So assume that this is what we randomly picked up. Okay, so we call this as the current state. Now the algorithm, what it should do, it should identify a neighbor. It should identify the neighbor of better cost. Okay, so what are its neighbor? This is one neighbor, this is another neighbor. So out of these two neighbor, which has the highest value? This neighbor has the highest value. Okay, so it picks up this neighbor. Now it checks the value of this neighbor. Is it greater than the current state? Yes, it is greater than, because it's going up. So in that case, make this as the current state and discard this. Again, repeat this. Now from the current state, identify the neighbor with the highest value. There are two neighbors. One is this, one is here. So again, this will be selected. So So again, is this neighbor value is greater than the current state value? Yes. So once again, this becomes the current state. So on and so forth, it continues until it reaches this global maximum point. After reaching the global maximum point, local maximum, until it reaches the local maximum point. After it reaches the local maximum point, it cannot go anywhere. It cannot move either this direction or this direction. Now if it moves this direction, it is less than the current state. So only this will be returned. If it moves this way also, this is less than the current state. So only this will be returned. Okay. Are you getting? So this is the case if initially the algorithm started from this current state. But say that if the algorithm starts with this current state, initially we are generating the current state randomly. So if this is the current state, then what will happen? Then in the next state, algorithm will identify this. So is this neighbor is better than the current state? Yes. So this will become the current state. Again, it will find the next one, so on and so forth until it reaches this. So now it will identify the global maximum. Okay. But the probability of that is very less because there will be only one global maximum. So randomly you choose the correct peak. It's very less. So most probably the algorithm will identify some local maximum. Right. Okay. So what are the advantages of hill climbing algorithm? So the successors are searched in a systematic way, right? When choosing a highest valued successor break, in case of tie, you can choose something randomly. Say for example, there are what the algorithm says, from the current state you identify the neighbors who is having the best value. Say more than one neighbor is having best value. Say there are two neighbors. Say this is neighbor 1, neighbor 2, both are having best values, both are having equal values, and they are the best. Now which one should you choose anything randomly. So in case of tie, randomly one node will be chosen. So ignore n1, take n2. Okay. Now is it better than cs? So then make this as cs and remove this. So that's what it says. And hill climbing algorithm can be used for both maximization problem and also it can be used for minimization problem. Okay. So it's not only that maximization problem, it can be used for minimization problem also. So in most of the real world problems, it will be minimization problem, it won't be maximization, because cost we want to reduce. Okay. If you see time complexity, we want to reduce. If you see space complexity, we want to reduce. So the algorithm for minimization also, the logic is same. Only thing it should always try to minimize the value instead of maximizing. Okay. So in this case, if it is so this is for minimization. If it is maximization, instead of less than or equal to, you have to make is greater than or equal to. So then we want to choose a neighbor which is less than the we want to choose a neighbor whose value is less than the value of the current node. So that's the difference. Okay. Fine. Now let us take the example of 8 queen problem. So this is how we define the 8 queen problem. So what is the state? Any arrangement of 8 queens on the board. So it can be of they can be placed anywhere. That can be treated as the current initial state or the current state action. So action, there is a restriction on the action. Move a queen within its column. So for action, we are giving a constraint. That is, each queen can be moved only within its column. Each queen can be moved only within its particular column. They cannot be moved in row wise. They can be moved only in the column. So for example, say already a diagram is here. So for example, there is a queen here. This queen, it can move anywhere within this column. Okay, it can move anywhere within this column, but it cannot move either in the row or in the diagonal. Similarly, if you see this queen, it can move anywhere within this column, but it cannot move in the diagonal position, right? So in that case, so what are the, how many possible moves each queen can have? So this queen can have 7 possible moves because there are totally 7 columns, right, or 7 rows. So it can move to any of the it can move to any of the other row. So it can move to the, in this column it can move anywhere. In this column it can move anywhere, but it cannot move anywhere else. So here there are 7 positions, remaining 7 positions are available. It can move to any of the other 7 positions. Already it is in this position. So with that it is 8. So this is applicable for all the queens. So this queen also, if you take, it can move to any of the other 7 positions, right? So each queen can move to any of the other 7 positions. So totally there are 8 queens, right? So there are 56 possible successor states. So how many possible successor states are there? There are totally 56 possible successor states out there, because each queen can move to any one of the 7 states. So what is the goal test? 8 queens on the board and none of them got attacked, right? And this is the evaluation function. Here the evaluation function is number of pairs of queens that attack each other. So that is what we define the evaluation function, right? So how many pairs of queens were attacking each other? So that is the evaluation function. So here what is our objective? Our objective is to minimize, because attack should becomes what? So when the goal test will be satisfied, when the attack becomes 0. So evaluation function is basically cost here. Evaluation function is cost. It is number of pairs of queens that attack each other. If one pair of queen attack each other, it is cost is 1. If 2 pairs attack each other, the cost is 2. But at last we want a board position where none of them attack each other. So we want to make the cost to 0. So it is basically a minimization problem. So we should find a state that minimizes the evaluation function. Okay. So it depends on the problem. In some problem we may have to minimize, in some problem we may have to maximize. But mostly it is like minimization. So you may wonder, what is this diagram? There are many numbers here. So actually this board position, so these numbers, what is that? I'll tell later. But this board position contains 8 queens. Of course, this is not a solution. This is not a solution. There are many attacks are possible. So here the score of the evaluation function is 17. Here the score of the evaluation function is 17. What is the evaluation function? Pair of queens that attack each other. Evaluation function is a pair of queens that attack each other. So that is the evaluation function. So the evaluation function value for this board position is 17. So it means that there are 17 pairs of queens that attack each other. So here there are 17 pairs of queens that attack each other. Okay, we can verify that. So first let us take this queen. So this queen is getting attacked with how many queens? So here it is how many pairs of queens that attack each other either directly or indirectly. There are some indirect attack also. So now pair of queens that attack each other either directly or indirectly, right? So if you take this queen, it is get attacked by this queen directly. It is get attacked by this queen indirectly. Indirectly in the sense, if this queen is not here, then this queen can attack this queen, right? So let us count. So it can be attacked by this queen. It can also be indirectly attacked by this queen. So 2. This queen cannot attack this queen. This queen can attack this directly. So 3. This it cannot attack. This queen cannot attack. This queen also can attack this queen directly. So for this queen alone, there are 4 pairs of attack possible. Okay. Pair in the sense, if this is attacking this, then this also can attack this. So we call it as pair. Okay. So now this we will remove, because this queen's attack already be calculated with all other queens also. So totally it is 4. So remove this. Let us not consider this. Let us not consider this. Now similarly do check for this queen. How many pairs of queen that attack this queen either directly or indirectly? This queen can attack directly. This queen can attack directly. This queen it can't attack. This queen can attack. So totally we'll count. This queen can attack directly 1. This queen can attack directly 1, 2. The second, this cannot attack. This can attack directly 3. This can attack indirectly 4. This cannot attack. So here this queen can get attacked by 4 other queens. So now remove this also. Similarly do for this. This queen, it can't be attacked by this queen. It can be attacked by this queen directly. Okay. It cannot be attacked by this queen. It cannot be attacked by this queen. It cannot be attacked by this queen. So its value is 1. is attacked by only one coin, right? Now remove this also. Now take this coin. So this can be directly attacked by this queen 1. It can be indirectly attacked by this queen 2. It can be indirectly attacked by this queen 3. It cannot be attacked by this queen. So it is 4. So how many queens can attack this queen? It is 4. Okay. Now remove this also. Similarly, if you see this queen, it can be directly attacked by this queen. It can be indirectly attacked by this queen. It cannot be attacked by this queen. So it is 2. If you see this queen, it can be directly attacked by this queen, and also it can be directly attacked by this queen. So again it is 2. Now remove this also. If you see this queen, it can be directly attacked by this queen alone. Okay, nothing else. So so remove this. So it is 1. Okay. So this queen already we calculated for this. So nothing, right? So now if you add all these things, 4 plus 1 5, 5 plus 4 9, 9 plus 3 12, 12 plus 2 14, 14 plus 2 16, 16 plus 1 17. That is how we got this 17 value. Okay. So that is the evaluation function. So here this evaluation function is also sometimes called as heuristic function. So its H score is 17. That is, for this board position, the H score is 17. You can call it as either heuristic score or evaluation score, but our objective is to make it to 0. Right? So fine. So now if you see, so now what these numbers are, okay. So these numbers, what it represent from this current position, if you move this if you move this queen here, then the H value will become 16. That is what the 16 says. Okay. If you move this queen here, then the H value becomes 16. Again it will be 16. If you move this queen here, then it will be 18. If you move this queen here, then it will be 14, so on and so forth. So if you are not moving this queen, but if you move this queen here, then the H value will be 13. If you move this queen here, then the H value will be 15. So basically it shows the H value. If any one of the queen moved to a different location, what will be the H value based on our constraint that the queen can move only in that particular column, right? Okay. So this is just an example for what you call the how the local search algorithm, the hill climbing algorithm, can be solved. So this is one board position. So now you have to move to a better board position. That is, you have to move to a better position which minimizes the evaluation function, because our objective is to minimize. So anything which is less than 17 is fine. So either you can move this queen here, or you can move here, but you cannot move here. So any queen you can move such a way that this evaluation function will become less than 17, and keep continuing this process until you reach the goal state. So for every location you have to calculate this. Okay. But there are some disadvantages with the basic version of the hill climbing algorithm, or there are some shortcomings. So what are those shortcomings that we'll be discussing now? So these are the primary shortcomings. The basic version of the hill climbing algorithm may get stuck because of this reason. It may stuck up due to a local optima, or it may stuck up due to a plateau. Okay. So what is a plateau? We will discuss. So, or it may get stuck up due to ridges. Okay. So plateau can be it is like a flat area. Like in the diagram we have discussed the local optima and shoulders. So they are called as plateau. Okay. What is ridges? So again, this is the same diagram which you already discussed. Ridges is something like this. So ridges is continuous local maximum. You are getting continuous local maximum. See, this is one local maxima. Immediately after that, you get another local maximum. Immediately you get another local maximum. So that type of area is called as ridges. So in a normal plane, we can draw ridges something like this. If you have continuously like this, okay. After that, there is a local maxima. Then there is a global maxima. Okay, but this type of area is called as ridges. So it is constant. It is up and down. So up also, it's not a decent up. It is not even worth of a local maxima. It's very small. Okay, so this type of area is called as ridges. Okay, so I mean, so this is with respect to the what you call the real space in the world. But sometimes your solution space also something like that. You may get a better solution, then worst solution, then better, then worst. And this better solution also, it is not a reasonably good solution. Its value is very less. So if the algorithm gets stuck in this type of region, so that is called as ridges. Okay, so now the problem is, here we are seeing the whole landscape. So we are able to understand that, okay, here is the global maxima, but in reality you don't have this whole view of the problem space. Okay, you have only the current view. Currently wherever you are, only that view you have. And so you have no clue, like how much should I move in which direction so that I will end up in global maxima or local maxima. Where, which direction I should move? Should I move right or left, or where should I move? All these you don't know, right? So that is the challenge. So the point is, this particular algorithm, this hill climbing, this basic version of hill climbing, steepest ascent hill climbing, it may get stuck either with local maxima. Okay, as we already discussed, for some problems local maxima is fine. But sometimes our objective may be to find global maxima. Then if it gets stuck in the local maxima, it won't move anywhere. It won't come down, because it will, because the neighbors are not better than the current state, so it will be here only. Or it may get stuck with a so this is local maxima. Or it may get stuck with a shoulder. This is a shoulder. Okay, or it may get stuck with a flat local maxima, plateau. Or it may get stuck with a ridges, right? So these are the drawbacks with the basic version of hill climbing algorithm, right? So here is an 8 queen problem with a better solution. This is also not a solution, but this particular board position, its evaluation function or H value is 1. Only one pair of coin is under attack. None of the queens are under attack. This queen, if you see, it cannot be attacked by any queen, I guess, right? Yes. If you see this queen, it is this queen also, it cannot be attacked by any queen. If you see this queen, this is also not attacked by any queen. If you see this, it's also not attacked by any queen. Yeah, this queen can be attacked by this queen. So that this is only one pair of attack, nothing else. This queen cannot be attacked by anything. This queen also cannot be attacked by anything. So its H value is 1. Okay, so what but the beauty of the hill climbing algorithm is, with minimal steps you can come from this state to this state. So here the H value is 17. Here the H value is 17. The heuristic function value or the evaluation function value is 17. Here the H value is only 1. So from moving from that state to this state, it has already actually taken only 7 to 8 moves, not more than that. Okay, so with less number of actions, it can move somewhere to a place which is close to a solution. But after reaching to that, it may get stuck. Now in this point, this is an example for local maxima. Now this algorithm, now this program got stuck here. It stuck with the value of what? H equal to 1. H equal to 1 means it is a local maxima. So for this type of problem, with local maxima you cannot satisfy, right? We are not talking about this type of problem where local maxima is fine. No, there are many real world problems for in which you don't want to go for an optimal solution, because optimal solution may be very costly. In that case, we can settle with a local maxima. But here We want a board position where all 8 queens will not be attacked. But if you evaluation function point of views, if you see, it has a very good H value. Its H value is only 1. So we want to make it 0. So probably there is no other board position. Even if you move any queens to any other, there are totally 56 possible positions. If you make all the 56 possible position also, may not be, you may find a solution. So this algorithm got stuck here. So it got stuck in local maxima, right? So this is the drawback with this technique. It may get stuck either in local maxima or in ridges or in plateau. Okay, fine. So now let us. How to come out of local maxima? Let us see that. So if the algorithm gets stuck either in local maxima or in plateau, how it should come out of local maxima? That's what we are going to discuss. So this is just an example for hill climbing for 8 queen problem. So let us start a randomly generated 8 queen state. So this 8 queen problem is started with a randomly generated 8 queen state. That is, the 8 queens are placed in different board position, right? Then we apply the steepest hill climbing as follows. So then we apply the steepest hill climbing. So when you apply the steepest hill climbing for the 8 queen problem with a randomly generated initial state, what is observed in the sense, 14% of the time it solves the problem. 14% of the time it solves the problem. That is, it is able to reach the goal state 14% of the time. And whenever it finds a solution, at an average, it takes only 4 steps. Is that clear? So we are discussing solving the 8 queen problem using hill climbing algorithm with a randomly generated initial state. So already we know that hill climbing, this is using steepest ascent hill climbing algorithm. This is a very basic version. It has certain drawbacks, like it may get stuck in local maxima, plateau, ridges, all those things. But in spite of that, when you apply this algorithm for solving the 8 queen problem with a randomly generated initial state, it can arrive at a solution 14% of the time. And whenever it arrives at the solution, at an average, it takes only 4 steps. Within 4 steps, it can reach the solution. But remaining 86% of the time, it gets stuck with local optima, like how here. So here actually this is gets stuck in local maxima. So remaining 86% of the time, this steepest ascent hill climbing algorithm, it gets stuck in local maxima. But whenever it gets stuck in local maxima also, at an average, it takes only 3 steps to get stuck into local maxima, right? So as a whole, either it will find a solution within 4 steps or it will get stuck in 3 steps. So that is good actually. Overall, it is good, because if it gets stuck also, we will stop the algorithm and we look for some other alternative. So it is not that it is running for 10 hours and 12 hours and then we came to know it is stuck. No, within a short period of time, we know that whether it will find a solution or not, right? So the point is, in this in case of 8 queen problem, the total state space is 8 to the power 8, because we have 8 queens. Okay, the total state space, and each of the 8 queens can be placed in. So we discussed that each of the 8 queens can be placed in, can be moved only with the respective column. So in one column, if you take, that queen can be placed in any one of the 8 locations. So totally there are 8 to the power 8 possible states. Okay. Previously we discussed 8 into 7, because next state possible is 8 into 7 possibilities for the next state, because already the queen is in one state. Already in each column, the one queen is placed. So excluding that, it is 8 into 7. But here everything is included. Total number of states is 8 to the power 8. Okay. So which is right. So that is different from this. Okay. So here, I mean, all these 8 queens can be placed in any location. So that's the point here. All these 8 queens can be placed in any location, which is 8 to the power 8. So that is 17 million states or possible. Right. Now let us try to understand, like, how to get out of the what you call, how to get out of the, local maxima. So if you want to get out of the local maxima, then we should allow sideway moves. So what is meant by sideway moves? Sideway moves means, assume that, so let us say this state space. Yeah. So assume the algorithm gets stuck in local maxima. Say this is local maxima, so the algorithm gets stuck. Now, when you want to come out of local maxima, you should allow sideway moves. So you allow sideway moves. That is, let the algorithm move in any one side, either this side or this side. Either it this direction or this direction, let it moves. So when it moves, no, there is possibility that it may go into a local maximum, right? In this case, it is not possible because now we know the entire state space, so it will go down only. It will go down only. Okay. But for example, if the algorithm is, if the current state is here, now you can allow the algorithm either to go in this direction or this direction. So if you go this direction, then you are unlucky. It will take you down. But if you go this direction, you are lucky. Not local maxima, you will reach the global maxima even. Right. So, but it all depends. But basically, how to come out of local maxima means the algorithm says allow side moves. So this is side moves, goes to the side. Okay. But again, there is a catch on this. You cannot allow unlimited side moves. Say, for example, we are allowing side moves. Currently, we are in this state. If you allow side moves and you are keep on allowing side moves, means the algorithm will keep degrading. It won't improve at all because it goes keep on going in this direction. So a better option is allow side moves with a cutoff. So the better option is allow side move with a cutoff, right? So what does that mean? Say for example, you allow 100 side moves. Don't go beyond that. You allow 100 side moves. If there is improvement, you continue. If there is no improvement, then see in the next direction. In next direction also, you allow 100 moves only. After 100 moves, if the algorithm is not performing well, then stop. Then you can understand that okay, this is not the correct place. Then randomly select some other state and start progressing from there. Okay. So that's what the whole idea it is. So when hill climbing reaches a plateau, it can be a plateau or local maxima, anything. Plateau is also a local maxima. There are no uphill moves. In that case, there are no uphill moves, then it stops. Alternatively, we could resort to a sideway moves. Okay. So it is not only in case of plateau. Sometimes, see, it is not only with plateau. Sometimes the algorithm here also say this is the point where you got L is equal to 1 for the 8 queen problem. Now we cannot improve further, but we want in this 8 queen problem, we want the final global maximum. We want a solution with L is equal to 0, where no queens are under attack. So here also this moving sideways is applicable, right? You can allow the algorithm to move sideways for a certain amount of time. Say 100 moves you can allow. If it is not improving, then see the next side, right? Here allow 100 moves. For example, here let us assume that after 100 moves it is going this way, then it is good, right? It is good because it is going towards the global maximum, right? So that's the whole concept it is talking about, right? So alternatively, we could resort to sideway moves, a move to a state which has the same value as the current state. That is in case of plateau. But in case of local maxima, it can be even the lesser, it can be even a lesser value than the current state. However, we have to be careful, but when doing so, you have to be careful that we do not get into an infinite loop, because sometimes we may get into an infinite loop, which is a complete plateau or a shoulder that never improves, right? And an idea that works in some cases is to limit the number of consecutive side moves. So this is an idea which is a good trick. So don't keep on moving in the sideway, but limit it. But put a cutoff on that. Okay. Right. So when we come back to our original example, so the original example what we discussed, 8 queen problem, randomly starting with the initial state, and if you apply the basic version of steepest ascent hill climbing algorithm, it achieves solution 14% of the time. Right. This is without sideway moves. So this version is without sideway moves. Okay. This is without sideway moves. But when we apply sideway moves for this algorithm, assume, so this algorithm 86% of the time it will get stuck in local maxima. So whenever it gets stuck in local maxima, if we achieve sideway moves, if we achieve consecutive sideway moves up to maximum 100, so we achieve sideway moves up to 100 sideway moves is allowed. In that case, the previous 8 queen problem, its success rate is increased to 94%. You can see this. So the original version of steepest ascent, when you apply the raw steepest ascent hill climbing as it is, its its success rate is only 14%. But when you allow consecutive sideway moves, when it gets stuck in local maxima, if we allow the sideway moves with a upper limit of 100 times, then these algorithms performance got increased to 94%, which is a very good improvement, right? Okay. So this is one way how, what you call, how the algorithm can come out of local maximum, right? And there are also many variations of hill climbing algorithm is available. So we will be discussing some of the variants here. So the first one is called as first choice hill climbing algorithm. This first choice hill climbing algorithm, what it does in the sense, it generates the successor randomly until one is generated that is better than the current state. So currently you are here, then it will generate. So there are, assume there are many successors out there. So there are 10 successors. Then it randomly generates one successor. Okay. How so it randomly generates some successor. How many times it will generate successor until it finds a until it finds a successor which is better than the current node, right? So that type of hill climbing is called as first choice hill climbing. It generates successor randomly until one is generated that is better than the current state. Okay. So you may ask, what's the difference between this and the original version? In the original version, if you see, it just selects only one. Then it checks whether this is better than the current or not. If this is better than the current, then we make this as current. Otherwise, the algorithm will return this. The algorithm will return this as the solution. But this is not the solution. So once again, it will randomly generate some other initial state and from there it continues. Are you getting? So that is the original version. But this first choice version, first choice hill climbing is not saying that. From the current state, you randomly generate a successor. Is this successor is better than the current? Yes. Then consider this as the successor. Otherwise, from this state itself, you generate another state. So on and so forth. Okay. Next is stochastic hill climbing. What is stochastic hill climbing? So stochastic itself means some probability is involved here. It chooses randomly among the uphill moves. The probability of selection can vary with steepness. So assume that this is a point where currently the algorithm is, or currently this is the current state, right? But from the current state, there are multiple uphill moves are available. Okay. Actually, you should visualize in the 3D space. So here we cannot draw in 3D space, right? It is a 2D space. So assume you are in a valley. Assume you are in a valley. So if you are in a valley, then what will happen? So you are in the bottom part of the valley. Then everywhere it's uphill only. You can move all the 4 direction you have uphill. If you move this way also it's uphill. If you move this way also it is uphill. If you move this way also it is uphill. It will move this way also it will uphill, right? So or let us assume even 8 directions. All the 8 direction you have uphill. Now the stochastic hill climbing, what it does, it will choose randomly among the uphill moves. So there are 8 possible uphill moves you have. Out of that, it will randomly choose any one and it will go in that direction. So that is what stochastic hill climbing does. Okay. So it depends on the number of uphills. So the probability of selection can vary with the steepness. So at what probability something is selected or something is not selected, that may depend on the steepness of that particular direction. Okay. So this stochastic hill climbing, it converges slowly than the steepest ascent. Converge means how much step it takes to reach the goal. So actually it takes more steps to reach the goal state than the steepest ascent hill climbing. That is the original version of the hill climbing. But in some landscapes, it finds better solution. but in some landscapes it finds better solution than the steepest ascent hill climbing. Okay, so that is, so every algorithm has its own speciality. So if you see this algorithm, its disadvantage is it converges slowly. Converges means it takes more steps than the steepest ascent hill climbing generally. But in some landscapes it can find a better solution than the steepest ascent hill climbing. And the advantage of this first choice hill climbing is it is a good strategy for states with many successes. So if a particular state has many successes, see here thousands of successes are there, then this is a good choice, because we randomly choose one successor. So it is highly likely that this may not be better than this. So you try again and again until you find a better successor. So then probably you may get into local maxima or global maxima, right? Okay. So similarly, there are another two techniques to avoid local maxima. One is called as random restart hill climbing algorithm. The other one is called as simulated annealing. So with random restart hill climbing algorithm, basically it works on this concept. What it says in the sense, if at first you don't succeed, try again. So generally we see this, right? Generally we say this: if you don't succeed, you don't give up. Keep trying until 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 you don't give up, you don't fail, right? So never give up. So this is something like that. If you don't succeed now in the first try, you keep trying. So that's what random restart. So the algorithm keeps on restarted, right? So basically it is a the random restart hill climbing algorithm conducts a series of hill climbing searches from a randomly generated initial states, stopping when a goal is found. So 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 you randomly generate an initial state. From that, you apply the hill climbing algorithm. Let it be the basic version. Apply the hill climbing algorithm. Say the hill climbing algorithm, it has if it reaches the solution, fine. But if it gets stuck in local maxima, then restart the algorithm. Then restart the algorithm with some other initial state. Now again continue. Once again, if it gets stuck in local maxima, again restart. And again restart in some other initial state, randomly generated initial state. But whenever we restart, we randomly generate initial state and keep restarting. So continue this process. How long you should continue? How many times we should restart? Until you reach the goal state. So that style of algorithm is called as random restart hill climbing algorithm. So with the probability approaching 1, we will eventually generate a goal state as an initial state. So when you keep on doing this, it is highly likely that sometimes directly we generate the goal state itself as the initial state. What does that mean? So in this diagram, if you see that, so every time we generate the initial state randomly, and then only the algorithm continues, right? So what if you are so lucky, or you tried many times? So if you generate an initial state, this itself also great, because obviously you will go here. But what if you generate this itself as the initial state? Then this itself is the goal state also. Okay. So when you perform this random restart hill climbing, eventually it may generate a goal state as the initial state, right? Because finally, if you keep on restart, at one point it should reach the goal state. So with the probability approaching 1, it will generate a goal state as the initial state. If each hill climbing search has a probability p of success, then the expected number of restarts required to reach a solution is 1 by p. Okay. So here, if each hill climbing algorithm has a probability p of success, if each of these algorithms, say we have restarted 10 times, if each of these algorithm has some probability, then the expected number of restart is 1 by p. How many times we should restart? That is 1 by p. Okay. Generally, this p value may not be same. If it is same, it is 1 by p. Right. Fine. There is one example here. Let us discuss that in the next class. We'll stop here. So, so to summarize what we have discussed, we are discussing about local search algorithm. So in local search algorithm, we don't mind about the past history. We don't mind about the path. We are only interested in the current state. Because for many real-time problems, we don't want the path at all. We need the current state or the goal state. Example is the 8 queen problem itself is an example. Or if you want to prepare a timetable, or if you want to prepare any roster or scan or plan or schedule, we want the final plan or we want the final schedule. We don't want like how we reached at that plan or how we reached at that schedule. That is not required at all. So in such cases, local search algorithm is more appropriate. And there are different types of local search algorithms. There are different ways in which local search algorithms can be implemented. So the basic version is hill climbing, and the basic version of hill climbing is steepest ascent hill climbing, which we have discussed. And steepest ascent hill climbing may start with local maxima or ridges or shoulders or plateau, all these things. And to overcome this, there are many techniques. So one of the technique is allowing sideway moves, and there are and the other technique is this random restart hill climbing is also a way to get out of the local maxima. And there are many different flavors of hill climbing algorithms available, like stochastic hill climbing, first choice hill climbing, all these things, right? Fine, let us stop here. Thank you.